Hi, my name is Alex Lopez, and this is my lab report for Physics 2211 Lab 5. I chose to do the falling slinky. So the purpose of this lab is to analyze the motion of a slinky as it is dropped and falls to the ground, and this will be done by creating a computational model to graph the motion using the forces that we know to be acting on the slinky, and then comparing this to a graph of the observed motion of the slinky. The main physics principle in this lab is Newton's second law, as shown above, and then using the net force to find the velocity update and position update. And the three different forces acting on the slinky are tension, gravity, and drag. Gravity always acts on it, and there's tension in the slinky up until the point where the slinky has compressed fully. And as soon as the slinky starts falling as one unit, there's drag acting on it at that point. And the interesting part with the slinky is as soon as he lets go of the top part, the bottom part will actually stay stationary as the top part falls, because the tension force pulling up on the bottom part is equal to the force of gravity pulling down on it. So the bottom part will just stay there as the slinky compresses, and then once it is fully compressed, it'll fall down as one unit and experience gravity and drag. Here are the initial conditions for the experiment. So the mass of the frisbee I found on the internet to be 0.218. The initial position is from tracker, and the initial velocity is just 0. Gravity is obviously 9.8, and the constant for the drag force I found to be 15. Here's the rest of the glow script code. So you can see we have two while loops. The one on the left, up until 5.5 seconds, is for the period of time where the bottom of the slinky is stationary and the top part is falling down to it. So you can see we have the force of gravity and the force of tension, which is equal and opposite to the force of gravity. So therefore the net force is 0 on the bottom part of the slinky, so it's not going to be moving at all during that part. And then on the right is for after the top and bottom parts meet and they fall to the ground together. So instead of the force of tension, we have the force of drag, which is opposing the force of gravity. And so that part is where the slinky will fall to the ground. And here's the resulting graph with the tracker data in the orange and the computational model in the blue. So the slinky in the tracker video didn't stay exactly still during the first section, but you can see where it did actually start falling to the ground in line with the computational model. And any other deviation is just most likely due to inconsistencies within tracker in tracking the position of the slinky. In conclusion, this lab demonstrates how multiple forces can affect an object at the same time and how that can change based on the state of the object. In this case, how tension was holding up the bottom of the slinky, and then once the slinky was fully compressed and there was no more tension, it experienced drag as it fell due to gravity. It would be interesting to replicate this experiment in a closed system with the slinky starting perfectly from rest in order to eliminate any factors causing the slinky to behave differently than we would expect. And overall, this lab gave me better insight on Newton's second law and the interactions of different forces and other physics principles.